Hi, this is Dr. Goldstein, and I am going to explain both the extreme value theorem and the intermediate value theorem. So first, the extreme value theorem states that if f is continuous on the closed interval from a to b, then there exist x values, capital M and lowercase m, in the interval ab, such that f of big M is the maximum y value of your function f of x on this interval, and f of little m is the minimum y value of your function on this interval. So just explaining some of the terms here. So extreme value in extreme value theorem means either a global min or a max. That's what we mean by extreme value. And so what this theorem says, basically, is that f has a global min and max. So f has a global min, which the value is f of little m at x equals little m, and a global max, f of big M at x equals big M. So that is the idea of the theorem, but it's very, very important that we have this condition on f. F has to be continuous, and we have to have this closed interval. So again, the idea is you have a global min and a global max as long as f is continuous and we are working on a closed interval. So an example of this is the function, the bit of the function that I have drawn here. So if this is our function f of x on the interval from a to b, including these endpoints, you can see that f is continuous. I can draw it without lifting my pen. There's no breaks, holes, or jumps. And if I look at this function, it looks like I have a global maximum right here on my graph. So that happens at the x value, big M, and the y value is this biggest y value that is f of big M. And that looks like that's right there. And it also looks like we have a minimum value right here. Oh, that's not very visible. We have this minimum value right here at this endpoint. So our little m in this example is also equal to our endpoint, and this f of little m is this y value that is the smallest y value that our function takes on. So that's a visual example of the symbols involved with this theorem. So the best way to understand something is sometimes to see a case where it's not true. And so that's what I'm going to show you next. Here's an example where the extreme value theorem does not hold. So notice if this is our function, it's not continuous because it looks like we have a vertical asymptote at x equals c. So here we know that the EVT, the extreme value theorem, does not apply because one reason is that f is discontinuous at x equals c. There is a vertical asymptote. Two, there's another thing going on here which is a little bit more subtle. You see how there's this open hole above b? What that means is that f is not left continuous at b. So f is not left continuous at x equals b And so our function is not continuous at b anyways. So really, if we wanted to see, and this is sort of an aside, based on this picture, where is f continuous? F is continuous on the interval from a, including a, to c, not including c, and also everywhere from c to b, not including either of those endpoints. So we don't have a closed interval that we're working on where a function is continuous. Okay, so what we see happening in this picture is that we are missing our maximum value. There's no maximum up here because our function keeps on going up to infinity, and so there's no one largest value. So the extreme value theorem doesn't apply, and we see that the conclusion of the extreme value theorem is also not true. So the conclusion of the extreme value theorem is also not true because there is no maximum y value f of m, f of big M, on the interval from a to b. Likewise, if we look for a minimum value, it would happen at b. This would be our f of little m, and so this would be our m, but that point is not included. So also, f of little m is not the min, since f of b, which is f of little m, is undefined. So we don't actually have that value in our function. Now, it's worth noting that on the interval from a to c, not a closed bracket, parentheses, the extreme value theorem still does not apply because our function may be continuous, but we're not working on a closed interval. So because the interval is not closed, and we don't have a maximum, but we do actually have a minimum on that interval. And let me show you where that is. So again, just if I'm looking from A to C, not A to B, this would be the overall lowest value on my function on that interval. So for this interval from A to C, this would be my little m. So we have this minimum f of m, the green one, at x equals a. But we still don't have a max. Because of that vertical asymptote. So on both of these intervals, from A to B and from A to C, the extreme value theorem doesn't apply. On the interval from A to B, I'm missing both my max and my min. On the interval from A to C, I'm just missing my maximum, but I do have a minimum. So when your theorem doesn't apply, you just don't know anything about the conclusion. It may or may not be true, but because the theorem doesn't apply, it's not guaranteed to be true. Okay, that was the extreme value theorem. Let's take a look now at the intermediate value theorem. So the intermediate value theorem says if f is continuous on this closed interval from A to B, then for any y value capital K strictly between f of a and f of b, there exists at least one x value c between a and b such that f of c is equal to this capital K. So I'll illustrate this for you in a picture, and I'll give you the idea. Why on earth would this be called an intermediate value theorem? What's intermediate about it? It seems hard. So if this is x equals a, here is our f of a. And if this is x equals b, then here is our f of b. And so what this theorem is saying is that I can pick any value for k that's between them, anywhere between them, and I will find some x value c, there it is, and notice that c is between a and b. And in this theorem, it actually has to be strictly between a and b, so you're not including the endpoints. For the extreme value theorem, you have to include the endpoints. For the intermediate value theorem, you're not including the endpoints. So the idea of the intermediate value theorem is that the function f achieves all of its y values between f of a and f of b, those are two y values, as long as it's continuous. So as long as it has no jumps, breaks, or holes. So another way of wording this is that f can't skip any y values. So the function f cannot skip any y values. So that is the idea that's the idea behind the intermediate value theorem. So again, the term intermediate comes from the idea that k is between f of a and f of b. It's an intermediate value. It's a value that comes in the middle of that. So this picture illustrates the intermediate value theorem. That function is continuous, and you can see I can pick any k I want. Here's another one. There's another k, and there's its c value. What's interesting to note is that I have to have at least one c. I could have more than one c. You don't really see that in this picture very well, but you could have. What I want to show you is what happens when the intermediate value theorem does not hold. So here's a non-example. Let's look at f of x equals 1 over x on this interval from 1 to 2, and we're going to consider the intermediate value k equals 0. K equals 0 is between -1 and 2, but that's not what we're interested in. We need this to be between f of a and f of b. So we need to see that. Is it actually between those? So in this problem, this -1 is your a and this 2 is your b. And so we check. We say, okay, f of -1 is 1 over -1, which is -1. And f of 2 is 1/2. And yes, k equals 0 is between f of a, which is f of -1, which is -1, and f of b, which is f of 2, which is 1/2. 0 is between -1 and 1/2. Okay, we're happy about that. But now if we try to find c, so we're trying to find c between -1 and 2 such that f of c is equal to k, which is 0. So we solve f of c is 1 over c. We try to solve 1 over c equals 0. If we try to multiply both sides of this by c, we get that 1 is equal to 0, which is not true. So this has no solution. So there is no c. So it looks like the intermediate value theorem is false because we have this value k that's between f of a and f of b, but there's no c value, so that when I plug it in, I get k. Well, hold on now. Let's look at our function. F of x equals 1 over x is not continuous at x equals 0. You cannot divide by 0. So in case you've forgotten, here's the graph of f of x equals 1 over x. So here's my x, here's my y, and I've graphed f of x equals 1 over x. This is discontinuous. At x equals 0. So it's not continuous on this whole interval from -1 to 2. So the intermediate value theorem doesn't apply. So we're not contradicting the intermediate value theorem, it just doesn't hold. Visually what's going on is here's the k value that we're dealing with. We're dealing with k equals 0. And if we look between 2 and -1, so here's f of -1, here's f of 2. That y value is between those two values, but your function skips over that y value. So f skips the y value 0. So this is an example where the intermediate value theorem does not apply, and you can see that when you try to find this value for c, you don't have it. Okay, so that is the extreme value theorem and the intermediate value theorem. These are two very important theorems in calculus, and I hope that you found this to be useful.